Charge me, I cuss a few more times.
All right. All right, we're on. So, like I said, I'll try not to go too loud and long today since there's no heat and I'm tired anyway. Let's see, last time we did a homework on servos, and then we talked about stepper waveforms and how a stepper works. So the usual review, right? If I look at a stepper motor, at any motor you have two parts. You have the stator and the rotor. The stator is the part that doesn't move, the rotor is the part that does move. So you learned in high school, if you remember, that a regular DC motor has two coils like this on its rotor. If you cut one open, you'll look at it, and it's got the shaft here, and then it has what's called a commutator there. That's two different pieces of metal. One connects to that one connects to that one, and then they kind of connect over here. So when you run current through it this way, this becomes a north and that becomes a south, and when you run current through it that way, then this one becomes a north and this one becomes a south. And the way what they do is they put a magnet here and a magnet here, and this is basically a south and a north with magnetic fields running through this way. So when you put power on and it wants to run through this way, make this the plus and that the minus, this becomes a north, the north, and this becomes a south. The north repels the north, remember magnets, so it starts to spin out of the way. It gets a certain point. If you look at this thing, it's actually shaped kind of like that. And you got what's called brushes that are just pieces of metal that ride on it here, and they're kind of spring-loaded. So they just ride on it like this. So if this is plus and this is minus, it gets so far around, and now it switches polarities. So this spins, it makes it about half the way around. Now it switches, and now this side's north and that's south, and it keeps pulling it around, and it gets around. Oh, now that side's north and that side's south, and it spins and spins and spins. So with a stepper motor, the magnets, the permanent magnets, are on the rotor, and the coils, they're usually drawn like this. There's usually a gob of them, are out on the stator, and so you have something like this with a north, south, so on going around. And you can have a unipolar motor, which, remember, this is the symbol for an inductor, or you can have a bipolar motor that's done like this. And usually what you'll see is, if it's a bipolar motor, they'll tie that to ground. I'm sorry, they won't tie that to ground. They'll tie that to the energized rail, and then they'll switch these to ground. Like so. So what we talked about last time is, if I make this a north, if I run current the right direction to make this a north, then he's going to step there. If I make him a north and a north, interestingly enough, this is called a half step, then he's going to rotate half, so I'll make an arrow there off of that south. So if I make this a north and that a south, that's going to lock into place right there like that. If I make this a north and this a north, then he's going to rotate over here like that, halfway in between. And then if I make him a south and him a north, then he's going to rotate on over this way. And so that's what we're doing. And what you find is there's half stepping, full stepping, and wave stepping. And then you can get into things called micro-stepping. So what I just showed here, go click, 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 is a half step. If I make it go bang, bang, that's a full step. And then when you do micro-stepping, what you do is in these coils, you adjust the current. So then you can get it. He's really, really south. I'm sorry, what was I using? I was using north before. He's really, really north, but he's just a little bit north, so now it's going to point this way, not all the way a quarter of a step. And some of them, some of the controllers I've seen will go like 32 microsteps per step. They got there's special chips that you can buy from Toshiba and a couple other companies that do all this. But of course, the more microsteps, the faster you got to move it to make it to go the same speed, right? Now, one of the things you gain in doing microsteps is you smooth it out. So if you're doing full steps, it's and you can hear some of these things, these 3D printers going singing to you. It's because they're doing full steps or half steps most of the time. If you knock that down to 16th type steps, quiets it right down. But you pay. You don't get nothing for free, right? What you do is, because you're not putting as much current in the coils, you lose torque. Torque is directly related to how much current you put in those coils. So once you're moving, torque isn't such a big deal. But once you want to stop or start, change inertia hard and precisely, then you want the torque. So we talked about that. And I don't have it up on the screen so I can see it. So I'm going to get this completely wrong. 2, 3, 4. So if I half step, I'll come and he'll be on, and then he'll go low, and he will do this on these 4 coils, right? And this is in time. And he'll do that. So I run coil to coil to coil to coil to coil, but I'm only running one at a time. Now if I want to do a full step, now, or I'm sorry, that's called wave stepping. Crap, it's been a while since I've read this. So now there's another one where you can go this way. Like this, and this gives you full torque. So move things around. And then there's wave stepping, which is actually 6 waveforms going through, moving through. So the homework I gave you last week was to go to that video, take a look at what he said, how it works, write your own code to do it. It's fairly simple. It's maybe 50 lines of code. That basically you say, you define your pins. I actually defined them explicitly. In mine, I defined them by the color on the. I defined them by the color on the stepper motor. So I've got red, yellow, pink, blue, and orange, and so I defined I think, I don't remember which one's which on this. You'd have to look at the data sheet. One of these is ground, and the way this motor's made is those 2 center taps are tied inside to the same pin, and then you've got the 4 edges of the coils coming out. So this is the stepper motor we were looking at with the driver for it. This driver is simple. It's a series of Darlington Pairs, which I'll explain here in a minute. But this is a 200 step per revolution motor inside of here, so 1.8 degrees per step. but then it's got a series of gears here, so it's called a gear motor head, and it becomes, can't remember if it's 1,024 or 2048 steps per revolution. And then they got little lights here that show you which phase is going on at a time. So if I really slowed this down, you can see each phase tick through as it was running. And then you can, by the same token, we ran it, I showed you how it moves from step to step to step. I can run it the opposite direction, step to step to step also. So, and I'm not using this on my regular board. So these things you can buy, I don't know if it's Amazon or eBay. It's a little plastic box. It's about this big. And it's got 5 of these motors and 5 of these controller cards. And at least, that's not it, but
probably close.
real similar. Yeah, these are, well, I don't know. This is different than the one I got. It's a slightly smaller box. That's a bigger box than mine was. But I think it was 5 motors, 5 of the cards, and I don't remember how many of these ribbon cables for like $15, $20.
All right.
It wasn't much. It's like $3 or $4 a motor, $5 a motor at the most. Now that chip that's on there is a Darlington Pair, and what a Darlington Pair, or it's a series of Darlington Pairs. So, real quick, if you remember, we talked about BJT transistors a long time ago. That's a BJT. That's a not pointed in, which is N-type material, P-type material, N-type material. And if you remember, this is the collector base emitter. And so IC is equal to beta, which is a factor of this, IB, and then IE is equal to IC plus IB. So this is a valve. It's a leaky valve. In hydraulics, it's called a pilot valve. You use hydraulic pressure to open a hydraulic valve. Here you're using electric current to open up a current valve. And you're adjusting how much the current flows. Now granted, if I put 10 amps into here, it's not going to pull 10,000 amps out of the top. It's going to turn into smoke if it does. And it all depends on what your power supply and whatever else can support. Now usually we'll use these as an amplifier like this. So we'll take a takeoff right there. And there's a multiplicative factor and voltage conversion and fun stuff like that. But what we primarily do in the microcontroller world is use this as a switch. So I put a little resistor here, and my microcontroller sits here and drives a digital I/O right there. So now I've got, let's see, this is usually 0.7 volts, and this is usually 5 volts, so that means this thing, you say, I want this to be something reasonable that's not going to burn things up, call it. These things don't like to draw more than about 10 milliamps or so if they can, depending on the chip. So if that's 10 milliamps, beta's 100, then this is like 10 microamps or so, and then this is sized accordingly, and that way you don't blow things up. What you do with a Darlington Pair is, now I take, I'm not going to be able to draw this well like that. I have a transistor and I have a transistor. Now what that does is, before the current amplification was beta, but if they're both beta, beta times beta, my current amplification is beta squared. And for a little bit of current in, I can get a gob of current going through like a relay. And that way, the most that my microcontroller can even dream about giving you on one of these pins is maybe 25 milliamps. And what these stepper motors are wanting is more along the lines of 100 milliamps. So we can basically multiply that through and get what we need. So that's what's going on that little chip. On that little driver board, there's 4 of these, I think there's actually 6 of those Darlington Pairs, and you're only using 2 of them. But if you look at it as that's the Darlington Pair, and that's a not symbol, so it's driving to ground. I've got my coil here and my coil there with that tied to rail and that tied to rail, and one comes here, one comes there, one comes here, one comes there, and now your microcontroller has to drive each phase separately. Now, the thing that I was showing you guys earlier on my video, you didn't see it, I don't think. I'm using a different kind of stepper driver. It's the Toshiba chip that handles all this stuff and microstepping internally. On that kind, I think it's Toshiba TB6600, but I'm not sure. You just have a chip, and it takes on its inputs. It has an enable, it has a direction, and it has a step input. And then it handles all the driver stuff on the back side. And if enable's turned off, then it doesn't put anything out there, and you can just freewheel. You can, well, these little gear motors you can't turn because there's so much gearing in there, but you can just turn it, and then you say if direction's high, if it's enabled, every time, I think it's every clock edge, it steps. It goes to the next step. And if direction's high, it goes one way, and if direction's low, it goes the other way. So now, instead of having to control 4 different things, now you can control 3 different things with a lot more precision.
So digital on-off to step.
Yeah, and most of the things that I've gotten are actually, it's really nice because a lot of the stepper motors don't want to use 5 volts. I mean, a good stepper motor is using 12 or 24 volts, and so you're not tying direct, you'll let the smoke out of something. Yeah. So they actually have an opto isolator in there. So inside the boundary of the box, they have these going on. You've got like, I think the one I'm using at home is 9 to 24 volts, and I'm running 12 volts in. So that's here, that drives this thing at the 9 to whatever the right voltage is. And then this, we talked about this before, this opto isolator, there's no physical connections. There's no way for this 24 volt current to run back into your microcontroller and blow it up. So they have all this stuff built in. It's got a heat sink, all the stuff you need. The ones I'm using, they can actually source, I think 3.5 amps on a coil, so they can do a pretty hefty stepper motor. And they can do, I have to go back and look at my code to see what kind of steps per minute I'm doing on them, but they'll.
You're talking for the drawing?
Yeah, my fancy Etch-a-Sketch.
Etch-a-Sketch, yeah.
Yeah.
I think it was a SparkFun, but I'm sure Adafruit has something similar, but they have stackable Arduino driver boards that are addressable.
Yeah, they do. These though, it's a metal. It's a metal box. It's big, and the whole back side of it's nothing but heat sink. So it's for like NEMA, NEMA 27s and big stepper motors. Like you're gonna go and drive a real CNC with it type motors. So that's that, and geez, I guess you can see that this one's turning. So your homeworks were that's stepper 3, stepper 2, stepper 1 were to just do, there it goes, just write the simple code yourself to do it, and I can show you that code right here. Point this down so that people can see. You find this code all over online too. It's nothing original about it, even though I didn't cheat and look online. I could have. So I'm going to explain something here though. So I've created a disable function that I can actually turn the outputs on and off. So I've defined my blue, pink, yellow, and orange wires. I just call them blue, pink, yellow, and orange. And I've got a clockwise, counterclockwise function in there. And that's it. I switch. What I've done is I've created a variable called phase. So it tells me which one of those phases I'm supposed to be in, and there's 4 phases, right? We had the way it stepped through. So if it's phase 1, I do this. If I'm at phase 2, I do that. 3, 4, back to 1. And then I have a little function over here that I use to choose the phase. So I'm going to tell you about a C. This is ANSI C and ANSI C++. We talked about our different variable types, right? And we talked about a car. We talked about an int. We talked about a float. There's some extended types. There's a byte. Bleh. I usually type and do in block letters, if you've noticed. A byte is an unsigned car. So now we see that we have a modifier, right? If I look at any one of these, this 8 bits, 2, 4, 6, 8. The normal way the C compiler will treat things is if they are signed variables, which means things are stored in 2's complement. I'll let you look up 2's complement to see what that means. But from a programming point of view, not caring about this stuff, it means your range is minus 127 to, minus 128 to 127. 256 steps, including 0. If I say it's an unsigned car, then it treats this as binary, which means that my new range is now 0 to 255. So this is unsigned, and this is signed. On an unsigned, 255 plus 1 is equal to 0. Because it's going to wrap around and those are all going to become zeros. It can't hold a bigger number. It's just going to increment. And basically you lose the 1 that would be over here that would make it 256. On signed, 127 plus 1 is equal to negative 128. Again, it rotates over, but now it looks like a 2's complement minus 128. And remember, we were taking advantage of that on a couple of the, advantage of this on a couple of the things. It's I don't have to go up there and say, oh, now you're equal to 0 again. I'm taking advantage of the fact that it's going to roll over because I know how my hardware works. And so I can simplify some things. But you need to write it in your code as a comment to say this is what I'm doing so that when you come back later, you know what the heck it was you were doing.
Yeah, someone takes your code and puts it on a 16-bit system.
And then it's going to do something totally different, right? So byte and car are 8 bits, and int is 16 bits. I don't know if they use it, if a double is available in the Arduino base language or not. A double would be 32 bits normally, but it might deprecate back to 16-bit. A float is a floating point number, and I think floats are 16-bit floating point numbers. And a double is an extension of a float, so that'd be 32 bits. And then the an int, now there's a long int. That would be 32 bits. Change your precision. You can do a lot more with it, but because the computer has to do because the microcontroller has to do a lot more steps, because it's only an 8-bit machine, to work on 32 bits, it really slows it down a lot. Not that you might notice depending on what you're doing. So now we're talking, what I'm getting in is to some of these specifiers that tells the compiler something about what this thing does. Now, I told you use something like a pound define everywhere, because that's what I grew up learning, pound define. What did I use? Yellow, 8. If I do that, what's going to do is the compiler is going to come through and it's going to say, oh, anywhere I see the word yellow, or this string of characters yellow, I'm going to put the number 8. So now I don't have to go down here and change 8 in 100 different places when I say it needs to be 9 instead. I just change it once, all the yellows change to 9. What they would prefer you do, pound defines are sort of deprecated in newer, which means, yeah, you can still use them, but we don't really want you to. They want you to use const. And then whatever it is, so I could fit a car in there. Const means it's a constant. It's not supposed to be changed. If we don't change it, nothing can change it. 6 of one, half of a dozen of the other, as far as I'm concerned. Down inside the compiler, there's some semantic differences that honestly I'm not really clear on what the semantic differences are.
I did a little reading and now I've forgotten half of it, but the short version of what I remember is, so like you said with the define, it's going to go through before it does anything and replace that with whatever the value is. So if you had something that was a large value or a large structure, you're going to end up taking up more program space because it's going to replace that everywhere it appears. Like an 8 isn't a big deal, but if it was something bigger, you're going to end up copying that to every place in your code, where a constant, it stores it in
like
a separate chunk of memory, and yeah, everywhere
Is a
that
pointer back to
exists.
that.
So it's only going to exist once, and it exists in a different memory space.
Yeah,
But
okay.
they say that there's times when
No, that makes perfect sense.
there's times when you would want to use one over the other, not just because of the storage, but because of some things having to do with scope, where it might trip over
Scope and
itself
speed of
if you
execution
do it
and
the
things
wrong,
like that.
if you do it the other way.
Right, yeah, so according to what you're saying is, what it says is, instead of copying the number 8 in there, which uses up that number 8 everywhere in the program space, it's going to do a pointer back to
Right.
that thing, so it's going to pass a pointer every time.
For constants, yeah.
Yeah. So now the next thing we're going to get to, I'm going to talk about a static. So static car val equals 0. Constant car, empty constant car val equal 8. That's how that would work. Static. So if I have my function let me go back to use what they always use for this because it's just kind of funny to me. I have a function foo with a variable
bar.
bar.
Char bar.
Do I need to tell the joke to everybody? It's a military term.
Yep.
Foo bar.
Yep.
Fucked up beyond all recognition. All right,
And we just got that on tape. That's awesome.
there we go.
He said worse.
I caught a few already. It's the
He's
best.
definitely said worse.
I am ex-military, so
On tape.
starting to get too warm. Okay. So inside of foo, I have my curly brackets that brace and define the scope of the function foo. Now if I come in here and say, have we talked about functions at all?
A little bit. I mean, you've obviously shown functions.
Okay, so up in my main program, I can call foo of 8. And so down here, inside of foo, I have int var equal bar. And maybe I've got something here. I'll leave it at that for now. So I'll actually do this. I'll say int var equals 0 to initialize it, and then I'll say var equal bar. And we'll make this a, that's not going to work because that's going to choke on that. It's a car.
Yeah.
I mean, it would work, but, and this is going to return a car. So now I've just defined foo as a function that will return a car, and it accepts as an argument bar, which is also a car. And if I come down here and say return var, now this is a really worthless function, but so the compiler is going to come through, and everywhere it sees this function foo called, depending on how you have your compiler settings set, it could A, take this whole function and put it up here in the place of foo and replace bar with 8, and that's called inlining your functions. So you would do that for speed, because now it doesn't have to do an address call off into a different address space. If you're doing something, if I have an int, if I'm doing something 7,000 times, wow, I can just do that, bang, 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 bang. I do these things 7,000 times. What we normally do is we don't inline our functions. In fact, to do that, I think you would normally also have to call this an inline car foo. That tells it it's inline. But you can set that in your compiler settings too. What this will do is this will set this piece of code off in a program memory space somewhere. And when you get to this point in the execution of the code, what the compiler will basically do is say, go to there. So now it skips all the other lines of code that might have been there and comes and puts that 8 there, runs all the code, and then it comes back, that return tells him to come back to the next line right after that. It's behind the scenes, or it's actually down at assembly level, so it's not a go-to, it's called a jump. What it really does is it hands off the program counter to the address counter off to a different point, but you bounce back and forth. So what this means is I've got this piece of address space over here, and it basically gets reinstantiated every time I go back into it. The compiler says, well, I don't need to keep any of these damn variables. I'm not using them. This is programs. This is data space that I can use for other stuff. So if I have car var equals 0, and I say, just erase this and make this a void, which means I'm not handing anything to it, but the compiler needs to know that for the function when it builds it. And I say var equal var plus 1 and return var. Now, so, blah, 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 foo. Foo. Foo.
Except you gotta remove your equal 0.
No, I'm gonna leave it there.
Uh-huh.
Print, let's see, x equal foo, x equal foo, x equal foo, and I'm just gonna say print x is pseudocode. What do I print out? 1, 1, 1. X equal 1, x equal 1, x equal 1. Because every time I go off into space, it's going to see that and reinitialize. If I didn't do that, if I just said car var, what would it print?
Does that clear the variable or not?
It's undefined.
Will it even work?
It will work. It's undefined. The way most compilers work, they go ahead and zero a variable anytime it's redone.
I was going to say it's very
That's-
specific to what you're.
That's compiler
Yeah.
specific. The C, I don't know that the C++ or anything else, but the ANSI C, the original Kernighan and Ritchie,
Yeah.
there was no requirement to clear out that memory space. So what you're going to get is just whatever happened to be in that chunk of memory last time added to 1.
Okay, don't do that in the PC world.
Yeah.
Yeah.
Don't leave memory with stuff in it.
Well, no, this is true. This doesn't matter what platform you're on. Now, so var equals 0, so that we set it. If I call it a static, this is a flag to the compiler that says every time I come in here, reuse this exact same piece of memory and don't update it. Don't re-clear it. So, with this static car var equals 0, now what's this going to do?
1, 2, 3.
1, 2, 3. So what you've created is a function that does things, but you don't have to remember where it was. You've created a variable that, I don't necessarily want to put a variable out here and have to pass it to that function every time and do all these things. Sometimes you're doing a whole lot of stuff and it doesn't make sense to hand that off and have all this other stuff manage it. You just say, you know what, go do your thing, and the function remembers where it was. If you think about the old spinner on the old DOS, where it would go between a backslash, a pipe, a right slash, and a minus and sit there and spin, it's basically a function that had a car and it was going through 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4.
I manually created that in scripts for Linux.
Yes.
Because it's very useful to see it's actually still
Yes.
alive.
So the whole reason, yes. So the whole reason we ran down this is so that when you look at my code, if you ever do, whenever I get around to posting it online, you'll see that I have this function that says, I don't know what I call the function, steps, that asks for phase and void. And it does the stuff to set the 4 bits to push the motor into the right phase, and then it says return with no return value. And what I'm doing is I've got another function right before it that says phase equals choose phase. Phase, comma, direction. And so what I'm doing, instead of having to put this big for loop out here that I have to call every time I do something, remember, if you do anything more than once, put it in a function and stick it off somewhere, and now call a function. Because otherwise I was going to end up with this thing where I'd have 4 of these, I'd have to have this big set of logic that says, well, is it doing this? I do that. If I do this, I do that other stuff. Now I can just say, hey, go to the right phase, go to the phase I want you to go to, and over here I'll choose the phase. And so if I'm going forward, I choose, if I'm on phase 2 and the direction's forward, then the next phase is 3, but if I'm on 2 and I'm going backwards, then the next one is 1. And it figures all that out for me and kicks it back. Life just got a whole lot easier to read. I'm going to share something else with you. It's called a switch function. Switch case. So you've got if something, else something, which can be another if, so on and so forth, and a whole gob of. There's something called the switch function. Switch. Variable. Switch X. And then you brace this open, and then it's case 0 lines of code. You need to bracket these also. Lines of code. Actually, you don't have to bracket those. Lines of code. Break. Break works anywhere. Break breaks you out of the current scope of code that you're in. So if you have a for loop and you get a function and there's a certain reason why you might want your for loop to break out before it's actually finished, if a conditional's hit, you use that break to pop out of it. So case 0, case 1, lines of code, break, so on until you get down to it's not a case, it's just default. And the default is the catch-all. If it's not 0, it's not 1, it's not whatever, then you go there.
Yep.
And you always want to put a default in because sometimes you get things that aren't supposed to happen. And then really weird things happen and you're sitting there clueless as to why in the heck they happened. Now, on some, I don't know the truth of this. A compiler that I used to have a long time ago would screw these all up if they were not in numerical order. On that compiler, it had to be least to biggest number. I don't know if I got in the habit to always put them at least to most.
And don't know about Arduino, but on some you can omit the break if you want it to do to the thing. So like if if you're case 0 and case 1.
Right. So yeah, let's do this. That's exactly true on everything. So case 0, case 1. If I want this stuff to happen no matter what, so break breaks me out of the switch. So case 0 happens. If I throw a 0 in there, I do this and then I break out. If I throw a 1 in there, I do this and then I break out. If I omit this break, if I throw a 1 in there, I go to here and do this and break out. If I throw a 0 in there, I will do this, and then I will do this, and then I will break out. You've got to have the break to get you out of it. That can also screw you up. That's those things that you look at and why doesn't this work? Why doesn't this work? And you look at it and look at it and look at it. It's, oh, there's no break in there.
Okay. It does look like you can do non-numeric ones, which some languages support, some don't.
Some compilers support, some compilers don't.
Yeah.
It's I have found that if you use I'm not going to swear to this because I don't have it right in front of me and I can't fiddle around with it. On the Arduino IDE, if you say case the letter A, it won't work. instead you have to pull out the ASCII for the letter A, which is
65.
is it six? Might be 60.
This has some kind of label thing
I was-
that you can do as well. It looks like they're not necessarily like in quotes like a value. I don't know.
No, label is what that's called.
Yeah.
It's a number. It's a number.
Constant allowed data type in int or, oh, it's saying in int or char.
Okay.
Yeah.
Labels constant allowed data types int and char. So you could do an A.
Yeah.
So limited but not
Yeah.
strings.
Yeah. Well, not even string. I've had no luck doing A.
Yeah.
I've had to actually go in and
And
write
do the
whatever
ASCII.
the ASCII equivalent is.
Yeah, wow, interesting.
And
Right.
I know everyone hates PHP, but one fun thing you can do in that, not that that's the topic here, but you can do switch true, and then each of your case could be independent logic that can be completely not related. It can just be, if this evaluates to true, do that. Could be if the sky is blue, if you're drinking Pepsi, if you're doing this.
I don't think you can do that in C. I
No.
could be wrong. I am no expert in C. So we're going to zoom back in over here again at my desktop. And we're going to see, so here's my, so all I'm doing right now, it's hard for me to see with these stupid glasses on, they're the wrong glasses for this. I say for count equals 0 to 4096, I delay a little bit. I tell phase to choose the next phase going clockwise and set steps to the phase, right? So it's exactly what I said I was doing. And here he is merrily spinning around, and you notice he's getting warm. He's been sitting here for a while. I'm putting amps into him, and that's power, heat. So even though it's cold in here, this guy's actually warm to my touch. And can you hear that? That's the sound of a stepper motor. Zzz, running fairly quickly. And down below, so I have these functions. Here's the set steps, and I'm using a case statement. Switch phases, case, tick, 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 tick. And down here's choose phase, exactly what I was talking about. Static, byte, state equals 1. So I'm remembering the state and doing something with it from the last time. And then I'm doing some funky math to make sure it's only ever returns a 1 through 4. But I'm doing it in a way that I don't do an if-then, which takes more clock ticks. I'm using a modulo function. Okay. So then stepper 2, your second homework, was to use the library. So right up here, we'll talk about this. Tools, sketch, import library. And so you can download the newer version of the IDE lets you go in and add a library, and it'll come in your list. But you can come down here and say, yep, there's the stepper library. I want to use that library. And it'll come right up here at the top, and it'll put the include file for the headers for you, include stepper.h. And so I've got basically the same thing. I've ripped out everything beyond. And I read their functions. I read their manual for doing this, and according to their manual, it says if you say go steps, you can set up the motor steps per revolution and what the 4 pins are, and then you set the motor speed to some RPM, and then if you tell it to go X number of steps and it'll go. And if you tell it to go negative steps, it'll go the opposite direction, is what their stuff says. And we can see it sitting there going and stopping and then going the same direction, so it's not reversing. So their code's not working the way it said it would in there. And I played around with a couple of different things and had no luck.
Oh, wow.
You try negative 1 times.
Yeah, and that might be what it is because I'm using a constant function there, and it might be screwing it up. And that did occur to me, and I just haven't gotten around. So we can actually try that right now and see if that negative 1.0, I guess that's negative 1. Where's my times? There we go. And let's see what that does.
Did it load? I think it loaded, but I'm not sure. Stopped for a second, and it's still going the same way. So, yeah, I don't know what's going on. And so then the third one is I got fed up with their stuff, and I completely rewrote it. And so this one does...
You rewrote the library?
I wrote my own library, basically. It'll do clockwise wave, it'll do counterclockwise wave, it'll do clockwise full steps, counterclockwise full steps, clockwise half steps, counterclockwise half steps. And so all of that's built in, and you see some big honking case statements here going down. But otherwise, and so here's what we're going to start. This is going to be our intro into what we're doing on this class. So in your Arduino library, or in your Arduino IDE, let me go ahead and upload this one. It's running. I'm going to say Tools, Serial Monitor. And whenever you start up the serial monitor, it will reset your board. But now watch. It says I'm going clockwise wave. Now I'm going counterclockwise wave. So what the serial monitor is a little serial port that's embedded into this thing that lets you talk directly to or hear back from your Arduino if you need it. So that's the first thing we're going to talk about today is serial. Serial is amazing. It is your friend. It is something that you don't want to use unless you have to.
And it becomes harder and harder every generation of laptop.
Well, yeah. So let's talk about the way Arduino works. Arduino, you've got your PC, in my case my laptop sitting here. And here on the side it's got a USB port. And I've got my USB cable. I'll be nice and I'll actually label it a USB cable. And then it comes to this giant Arduino. And that's a USB-A, I think, or is that a USB-B?
Most of them have the A, the square one.
That's the A and that's the B.
Yeah.
If I remember right.
I think that's right.
I think you're right.
So that's that's a B, I think. That's a micro, that's a mini.
Yeah, mini is the thick one, micro is the small one.
Micro's a small one. Now there's like a super micro or something like that. And this big clunky one over here that's like that big around is the A. So USB carries power. It carries 5 volts at less than or equal to 500 milliamps. It carries ground. It carries a shield to help just a overbraid around it to keep noise from going everywhere. And it's got data plus and it's got data minus, which is a twisted pair. It's 2 wires twisted up, some number of twists per inch. The reason that you do twisted pairs is they're less noise. And what happens, we talked about inductors and how inductors work. Basically what you've done is you've wrapped 2 inductors this way. You've got these 2 wires, so when current flows this way in one, it forces the other one to do current the other way. And so it has great noise immunity. And then you add a shield on top of that, and you've got a really great way to transmit data over some space. So this 5 volts goes off here to run all of the things on the board. Data plus and data minus go to an FTDI USB to serial converter. FTDI is a company. I bought their stuff. I have a friend who loves to hate them. They make a bunch of different. Products, but this chip is basically a full-up modem on there. If I remember right, it understands something similar to AT commands and some of the other things.
And what it does is on the Atmel, what the heck, on the Atmel, this is the microcontroller, is a 328P AT Mega. It's an Atmel AT Mega 328P. Inside of it, it has a serial. It has the hardware for a serial port, and that goes right there. Now, the FTDI USB to serial gives you serialized data in whatever format you choose. Usually 8-in-1, I think, is what they choose on the line by default. And you can choose in the IDE and the serial port what speed you want that to be at. Anywhere from I know it goes down to 2400. I don't know if it goes to 12 and 300 baud, all the way up to 115.2, which is the standard stuff that most modern, now old serial ports will do. RS232 signaling. So let's be a little bit clear about this. I'm going to misuse the words RS232. RS232, 0 volts. A high is anywhere between, I think, 1.5 and 12 volts. And a low is anywhere between minus 1.5 and minus 12 volts. What you'll see on a lot of things, there are some USB serial port dongles that you'll put together. They'll have this FTDI driver, and then they'll have another chip right there that actually has a charge pump and gives you, I think they go up to like 7 and minus 5. Or maybe it's 5. I think they give you 5 and minus 5,
Yeah,
which falls inside the RS232 standard. The other thing is, in the RS232 is inverted. A 1 is a 0 and a 0 is a 1. So let's talk about RS232 serial, which is CMOS serial. You usually have a data frame, which is a start bit, and then 2, 3, this is going to be hard to do. You have a start bit. You have between, I think, 7, 8, or 9 bits of data you can push. You have a parity bit, which is optional, and then you have, and this is interesting, you can have 1, 1.5, or 2 stop bits. So RS232, serial CMOS, you'll see a 0, and then it will go to a 1, and then it will have your data. So if I'm doing 8 data bits and it goes 1, 0, let's do it this way, 1, 0, 0, 1, 1, 0, 1, 6, 7, 0, I will see this. Parity bit, we usually don't use a parity bit. So what you usually see is 8 in 1, 8 data bits, no parity bits, 1 stop bit. So, okay, no parity bit, so that's X'd out. And then 1 stop bit, which is this, or does it actually go up? So what's going on here is you don't know when the start of a data frame is. And you've got a free running clock.
and it's asynchronous protocol. So what that says is on the sending end, I'm going to try and be this speed, but there's a little bit of slop. It might not be because it's not the same oscillator. They're not perfect. This guy's time is a little, my watch runs at a different speed than your watch. And if I sit here and say, okay, it's 1 o'clock, 2 o'clock, 3 o'clock, you might say, no, it's 1:01, 1:02, right? So the two clocks are going to be really close to the right timing, but they're going to be off from each other a little bit. And there might be some variation. So what happens is this first thing comes in, it says, I've changed the state, we're doing data now. And inside there's a little timer that's going tick, 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 tick. I've got all my data bits, and now it says, I know that's not a data bit, and I shouldn't get any more data until here. But what they found was a long time ago that even though everybody built to the same standard, everybody's hardware was a little bit different. And some computers wouldn't play with other computers because this relaxation time here that you had to wait and say there's nothing didn't quite work, and then they'd get confused and they'd start picking up bits in the wrong. They'd wait too long and they'd think, oh, this was the start bit, or they'd never get it, and that's the start bit. And so they did a 1, a 2, and a 1.5 got thrown in there somehow. And that was to adjust for timing between, say, HP and Sun computers, as a for instance. I'm just pulling stuff out of my butt. But that's why the 1.5 and the 2 came about.
How do you have half of a stop bit, though?
It's timing.
Time.
Yeah,
It's time.
yeah, now I get it.
It's what the dead time is.
Right, gotcha.
And so now we're getting to the difference between baud and bits. Your bits per second, it's not a P, bits per second is the total rate. So if I'm doing 8N1, that means I have 1 dead bit and 1 dead bit. So to send 8 bits down the pipe, I'm actually sending 10 bits down the pipe. My bits per second is 10 bits per second, but my baud is 8 baud. Baud is my signaling rate. These days, they're almost interchangeable. Back in the day of, 300 baud modem, well, I'm getting 300 bits per second, but I'm only getting 250-ish characters per second through.
It's a marketing thing.
No, it was because there's different protocols, right? If I'm running 8N2, then that bits per second stays the same, but the baud rate changes.
Yeah.
Now that I'm using Ethernet and things are running at gigabits per second, well, my data frame is maxed out at, I think a large frame is like 8 or 16 kilobytes. But my header can be 128 bytes. So, it's substantially, the bits per second rate is substantially higher. The baud rate is, because it's so fast you don't notice it, but the baud rate and the bits per second rate might be substantially worse comparatively, or they might be better because of max frame size.
And as we advanced in modems, the baud rates and stuff, they're talking about compression. There's compression involved there, and all kinds of crazy stuff.
We talk about things where we talked. I think I vaguely mentioned Shannon's law, Shannon's theorem, and Nyquist. This is a symbol. It can be a 0 or it can be a 1. Well, what if it's got 4 states, right? Now it can be a 0, 1, 2, or 3. And if I can tell them apart, and then I can screw with phase, and I can screw with frequency, and that's what, when you, the old modems, which we don't hear anymore, but you hear that, doing, that's them negotiating what I can do and what I can understand.
Yep.
And then you end up with this point cloud in space, and statistic likelihood of things being here, and they're sending basically 16 bits on a single symbol. Boom, things go fast. So now we're going to take a step back and talk about RS232. When I was doing my CMOS, I said, And then I've got a start bit here, start bit. In RS232, this will be reversed. So this is 0, this is 5 volts. This will be 5 volts, and this will be negative 5 volts. They'll be reversed from each other. And that works out really well on the receiving end because often you'll receive it with an opto isolator, and an opto isolator inverts things as it does it, and bang, your data comes out exactly the way you want it. That actually bit me on the butt recently because I built a board expecting this, but then we ended up using that. And so then we ended up having to pull out opto isolators and jumper things and do things screwy. Yeah. I was really surprised to find out that some of the USB to RS232 converters, some of them that you buy, the little dongle that you buy at Radio Shack, what comes out of the end is 8-in-1 CMOS levels, 0 and 5 volts. Some of them are actually RS232 compliant, and they have the charge pump, and they give you negative 5 volts out of the back of them. And I didn't realize that.
That's the great thing about standards. There's too many of them.
That's right. We're going to stick with a standard, but not necessarily the one we wanted. So now that we're here, this is how your computer talks to the chip. And there's some other stuff. There's a couple other chips on here that do some talking in there. But so now you saw me having data come back. In fact, it's still coming back from the stepper motor. It's coming up. What I'm doing is I'm talking on this serial port through here, through the USB, and into a terminal here. And it's all, it's invisible to me, but it's like I'm plugged in right there. Now, if I'm not plugged into a computer, I can still use these pins. These are pins right here, 0 and 1. Those two pins right there are those two pins over there on the board. So pin 0 is RX in. So this echoes out, pin 0. And this echoes out to pin 1. And so this is RX, and that's TX. Now, one of the problems you have with RS232 is that people talk about RX and TX, and you're like, well, wait a minute. Is that RX the pin that I'm receiving on? Or is that RX connects to your RX?
I have a little jig just for this problem.
So it's really nice if you're ever designing a circuit that instead of just saying RX TX, you say RX out or TX out and RX in, so that people can go, oh, that comes here. And they were nice enough to do that on these boards. It says RX and TX, but if you look, there's a little arrow that shows which direction the data is going. So the RX is coming into the board away from that connector, and the TX is going out to that connector. So,
because they knowing Arduino, you'd be able to program it.
So the truth is, I'm using ANSI-C, but I try to. But what I'm really doing is using a mix of C and C++, because the Arduino environment uses GCC, which is GNU C++. It's a GNU C compiler, which does C++, and the IDE, the Arduino IDE, is actually C++. But C++ is fully backwards compliant, as far as I know, with ANSI-C, so all my ANSI-C shenanigans work just fine. I don't have to do object-oriented code and
You mean forward compliant. ANSI-C will run in C++.
Yeah, whichever.
Yes, ANSI-C is older, so
Yeah.
and C++ is backwards compliant with ANSI-C.
Oh, yeah, okay, I got you.
TX
Sounded wrong in my head.
TX
Yeah, I was
and
going to
RX.
say TX and RX too.
Depending on your perspective.
Right.
Yes, yeah. So, where was I? Oh, so you don't have to include the library. It's kind of a built-in as a part of the regular libraries. Is a class called Serial. And I'm gonna have to look at some of my code here real quick because I don't
Just gonna
have it off the top of my head. Okay, so Serial is a class, and it has several different functions, and you can look that up on the Arduino reference website. But the first thing you want to is Serial. I think Serial's capitalized, isn't it?
So, yeah, S is capitalized.
So Serial. The first thing you'll want to do is begin baud rate. I think the Arduino serial terminal defaults to 9600
I believe
baud.
so.
Yeah, 9600 baud. If your baud rates don't match, you get gobbledygook. You get Chinese characters, God only knows what, rolling across your screen. So you want to make sure they're the same. So in your setup code, you'll set up serial begin baud rate, and then anywhere in your, what they call it, the loop code, which is down in main, in real life, you'll do serial dot print. There's print, there's read, there's write, there's
Print line.
print line, and I think there's actually some more.
Yeah.
So serial dot print line, read, write. Oh, there's avail. I don't have it on this. There's avail, or available, or something along those lines. You guys got it right there, so I'll let you look it up for me. You got the internet in your lap for all intents and purposes.
What does that do?
Available?
Yeah.
Let you know that there's a byte available.
Oh.
Yeah, available.
Is it available?
Get the number of bytes characters available for reading from the serial port. There's also available for write.
Yeah, okay, so I'm not gonna go into the what's behind here. Print is handy. Print, I can say some variable X, and I can just do that, and generally it will print it in decimal so that I can read it. Or I can specify, I can say X comma, say for instance hex. Somewhere that's a constant or a pound define or whatever, and that'll print it out in hexadecimal. It's got decimal, octal, hexadecimal, and binary, I think. So it will print that out. You can say print line. So if I say, excuse me, if x equals 3, and I say print x, what I'll get is 33. And then whatever the next thing I print is going to happen right here. If I use print line x, print line x, then I'm going to get 3.
I did not know that. I was doing /ns.
Backslash n. Yeah, it throws a carriage return at the end. You can print strings. You can say print blah, 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 and that'll poop out. I don't know if you can use the concatenate operators in there.
Supposedly you can, but I had some weird results when I did it, when I was mixing numbers and strings and...
Okay, I use ANSI because I know I have problems with this sometimes. There's,
Apparently you can use apostrophes for byte characters instead of the double quotes or something. There's some weird notation with the printing.
I think it's this way.
String
Destination,
Yeah.
source. String cat takes two strings, puts them together, makes one string.
Yeah.
But you have to make sure that the string that you put it, the memory that's allocated for the string that you put it in is long enough to hold them both. Otherwise, you get a buffer overflow, and then bad things will happen.
Yeah, just for completeness, the weird thing I was getting was it would print, I think essentially what I wanted, and then the next time it would print, it would be off a character, and the next time it would print, the next time it would print, until it would print a couple of blank lines, and then it would start spitting out garbage.
You were having
Yeah.
a buffer overflow in there.
But it was just using print line with concatenation, so like, it's like just print it, just do it.
The print is a great troubleshooting tool. You go into a function, my code's not working the way I want it to work. I'll go in, I throw a serial at print line, just a number 1 in there, and a number 2 over here, and a number 5 over there, and I see what numbers come up on the screen in what order.
Where's it failing?
Where am I making it to, and where? Oh, I got 500 5s. I should have never gotten any 5s, right? How did I get there? Right away, I have a clue of how to fix the dang thing, right?
Mhm.
So, prints your characters in ASCII so that you can see them on your terminal screen. So, we were talking about this a minute ago. It's 60
Is
is the
65
base.
is A.
65 is A.
Yeah.
Mhm.
So, 65
In decimal.
decimal
Yeah, 41
is
hex, I
equal
believe.
to, there it is. It's 40 that you subtract or something like that, is equal to the character A. So if I print A, I'll get A. If I print 65, I'll get 65. If I write A, I will get if I write an A, I will get something that's not readable, I think.
It's
If I
send
write,
a byte
it sends a byte. It doesn't
value of 45
right.
or of 65. sorry.
65.
The
So
example here is
a
45.
65 will go out, but a 65, it depends on the terminal. But if I write a 65 in here, and I write that byte, I will get an A.
I'm sorry, I was looking down. Yeah, yes, that's
If
exactly
I write a
it.
65, I'll get an A. If I write A, there's no telling what I'll get. It might treat that as, if I haven't defined A somewhere, then it'll see that as it'll instantiate some piece of memory and say, oh, well, where's A? I gotta send up here. And if I put it in quotes, I don't really remember exactly what happens, or be some weirdness.
Yeah, and like I said, there was something weird between double quotes for like a string and
Yeah.
single quotes for like a
Yeah, it's
byte.
saying right in double quotes will send the string in Arduino land.
But the single quotes.
It doesn't. It's not giving a single quote
Yeah,
example.
wherever I was
Yeah.
looking was talking about that, and it was.
So there's something else. So print, even in ANSI, print is a dangerous thing to use. Number one, it's an open-ended construct. It's an open-ended function. It can take effectively an infinite number of inputs to it, and it has code down in the libraries that parses the thing that you gave it, figures out what to do with it, and pukes it out. So the first thing is print is slow. Print is really slow. Next, on the Arduino library, they've stripped it out. it's missing a lot of functionality. So if you try to print a float, it will print nothing. So if you think that you're going to print the value of a variable at a certain point in time and it's a float, sorry, it's not going to happen.
Oh, nice.
It will print decimals though. Floats don't work.
But it lets you declare a float in other places? Because you were talking about it earlier, weren't you?
You can declare the type and you can use it just like a float, but it won't print a float. So there's
Well, that's
well, normally you don't need to print them out, right? Because you're on a microcontroller and you're not connecting to it.
That's almost worse to me. I'd just be like, well, then don't let you use it at
I
all.
think the difference is a little semantic. I mean, a float could be like this, and what it prints out might be.
No, it prints nothing.
It prints nothing.
Really?
It prints not. It prints. You might get a -1
Yeah.
for an error. There is another function. I was really going around on this because like, why the hell isn't this working? This auto work. I thought that was the whole problem. I thought that was the whole problem.
Get the debug output from print.
I thought that was the whole problem, that I'm doing the wrong thing and somehow not getting the right answer in there. And going through this, I'm like, no, this ought to be right. So I started looking on the internet. It's like, yeah, you can't do that. And there's another little function that somebody wrote that basically does a conversion and takes your floating point and turns it into a string, and then you can hand the string to the print and have the print puke it out for you. So yeah, that was annoying. So if you use the serial library, if I want to read, what you want to do is that you've got a loop and you want to accept data from wherever. You don't just want to do a serial read. What happens with a serial read is it goes out and it says, give me the data you got, and if it doesn't get it after a certain amount of time, it times out and returns a -1 to say it didn't work. When you're sending data down, you might be sending a -1. You might be sending numbers. -1 might be perfectly valid. You don't know that you didn't get what you were looking for. So what you want to do is something along the lines of if capital serial dot available greater than 0, then you do serial dot read, and that'll read a byte. And I think you can tell it read 10 bytes, read 20 bytes, read 1 byte, and you can have x equals serial dot read. So if you're wanting, so what you can do, and I have done this, is set up like little state machines, so that if I hit S, oh, I've got a byte available. I do an S. Oh, if I get S, I go into this case statement and do something. Oh, I didn't get anything, I just default and ignore it. Oh, I got an X. If I get an X, I'm supposed to do this. It lets me provide some computer interface to the Arduino to send commands back and forth and tell it to do things based on what I want it to do. I've made some cheesy test equipment that way, that I can say, oh, do this, and oh, calibrate yourself now, and zero yourself, and okay, give me data, and things like that. And it's perfectly fine for that kind of stuff. The other thing is, if you're using the built-in serial, it will always be on pin 0 and 1. Always. There's no way to change it. There is a library called soft serial. And with soft serial, you can choose your pins, I think. But the difference is, serial is using the built-in hardware that's already in the chip for you, and so it's faster. It sits there, listens to interrupts. When an interrupt happens, and oh, okay, I've got that byte gone. Okay, now I'll hand the next byte off. Soft serial is done all software, which means it grabs hold of timers and other things to make sure that it gets its baud rates right. And so soft serial, if you don't have to use soft serial, don't use it.
Looks like the Mega has 3 additional serial ports too.
Yeah, okay.
So
The
there's-
Arduino has only one. The Uno has only one.
Yeah.
So, soft serial is something you can look at if you don't want to use those 2 serial ports. For instance, if I want to talk to the computer, but then I want this thing to go off and talk to this other one over here. So I've got a computer talking to an Arduino that talks to another Arduino or something like that.
Yeah.
And maybe the
I
first
must have had a
Arduino
Mega-
is just
I must have had a Mega when I did sort of that exact thing, talking to another one.
Right, yeah, I've done games with 2 Arduinos, actually that little controller thing. The first Arduino does all the data collection and all this stuff and ships it up the road to the other one, and then the other one knows what to do with it, and then it does the stuff and spits it out to the right things. So, there's reasons why you might daisy chain something like that, and it makes perfect sense. So, that's the first lesson, and so your homework is going to be, for that, is something stupid simple along the lines of, print hello world. Just print it out. Maybe do a loop back. So with a loop back, you do a read available. If it's available, then I read it and then turn it right back around and write it. And if it's not, then you do nothing, right? So as soon as I type a character, oh, I got a character, I'll spit it right back out, back to the computer. So if you hit an X, you'll see an X come up right next to it. So, and that's the case where you need your local echo turned off if you're using a terminal. Speaking of terminal programs, if you're wanting to run your Arduino that way in sort of a, client server mode is not the right way to put it, but if you're wanting to control your Arduino that way, you're not going to have to open up the IDE to do that. Get yourself a terminal program. There used to be Hyperterm was part of Windows, not anymore.
Yeah,
Putty. I use TerraTerm. I've been using it for years. I quit using it for anything but serial when they didn't go up to SSH2. But TerraTerm's nice because it also does macros and recording. I don't know if Putty does that or not.
Putty's weird, but it works.
Secure CRT if you want to pay money.
Yeah, I'm only talking free ones.
Yeah.
I had it from I've maintained a license from some obscure thing I had to do. I think it was recording crazy functions and.
Yeah, TerraTerm was actually written by a Japanese guy, I think, because the original character sets were Japanese, but he made English available, and everybody really liked it because it had macros and everything. And I think it made it to version 4, and then I don't know. He said, "Screw this, I'm not doing it anymore." But somebody else picked it up, and it was all open. They sort of open sourced it, and it's still you can still download it.
I don't remember the one I used to use. I always hated Hyperterm. I used something else that actually had stuff built in for the Muds and Mucks, where it had like arrow keys and it would do north south. It had stuff built in for the games that were.
Actually, if you download TerraTerm and you tell it to, it'll install Cygwin too, I think.
Oh.
So now the other thing I want to talk about tonight. So we're going to do let's see, write this up here. Serial loop back. That's your homework. 1. Now homework. So now we're going to talk about analog to digital converters. It's going a lot longer. We're going to be 2 hours. An ADC is exactly what it sounds like. I have some varying value on an input. I turn that into some number between 0 and, on the Uno it's 10 bits, so that's 28 bits is 255, 512, 1024. Somewhere between 0 and 1024. And so what you get off the back end is you get a digital number that's a representation of whatever the analog input is. And you can do things with the Arduino. You can do I didn't look all this up, so I'm going from memory, from older memory. You have a function that's along the lines of set reference
and that can be, I think it's default. If you don't call it, the reference is 5 volts. You can call 3.3 volts, and then the reference is 3.3 volts. And I think there's a 1.2. And what this reference is, you got to be careful with this. So you've got your chip, you've got this input. This is the symbol for an analog to digital converter. So analog in and 10 bits of digital out. And so it's 10 bits, so it goes 0 to 1024, where 0 equals 0 volts and 1024 equals reference. So if you want to zoom in on something that's a fairly small voltage and get a good range on it, however, important, if I've set this to 1.2 volts and I stick 5 volts on it, you let the smoke out. There's a very good chance that you let the smoke out. If you set it to 3.3 volts and you put 5 volts on it, there's a very good chance you let the smoke out.
Wow.
Magic blue smoke.
And it might not actually let it all the way out. It might only let it part of the way out, and then you wonder why your ADC still gives you values, but they don't seem right. So the way the I've got time to go into a little bit of history. But let's talk about the Arduino first. The Arduino, the Atmel processors, this is a multiplexer. MUX, short for multiplexer. And this is actually an analog multiplexer. And then you've got 2, 3, 4, 5, 6 analog inputs, probably 7, 8, but they're not tied to anything. And so you can use control bits to choose which one of these lines you want to come into the ADC. And those on the board are pins. They're over here. It says analog in on this one, A0 through 5. Those are analog inputs. So if I've got 5 volts here and these are left open, let's see, I think there's an analog read function. I'm going to go back to my regular all caps. Analog read A0, or you can just say 0. And so if I do an analog read 0, 1, 2, 3, 4, 5 and print them all out, so I'm going to do a read, print, read, print, read, print, and I've got my reference set at 5 volts, what do you think my values are going to be coming out? So I'm going to read this one, they're all going into the same analog to digital converter. So I'm going to read, 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 read.
Sorry, is it going to be 1024 for the first and
Sure.
And then down?
There's nothing tied to that. Use this. It's a no connect.
Well, I mean, one would want it to be 0, but obviously it's not going to be, because otherwise you wouldn't be asking this question.
Smart man. What you've created is a time constant. This is a capacitive input. And the only way, once you switch this switch over here for this charge to leave, is either through the ADC or to leak its way through. And so you'll see, I'll go back to 5 volts and not 1024. You'll see like 5 and 4.8 and 4.6 or 5 and 3.2 and then I'll go back to 5 and as you're going through.
And the faster you do this, you can actually figure out the time constant. If you work, you can adjust the speed and whatever else. I'm not going to make you do something stupid like that. So this is how the thing works. And so it's important. I don't know if the analog read, the proper way, I'm an analog engineer who has been doing this for 20 years at really high speeds. The proper thing to do is, one, put a lot of amplifiers in front of this so that you drive these loads and you don't have this stupid time constant. Because if you have a high impedance output and a high impedance output right next to each other, this time constant is going to affect you, and you're going to get crosstalk between your analog channels. So you need to be aware of these things. So when we do an analog joystick, right, an analog joystick is usually a pot on X and another pot, let's make this X and that Y, and they tie these two together at ground, and they tie these up at 5 volts, and then this goes into one analog input and that goes into another analog input, and now you've got as much as, if this is 10K and you're reading right in the middle, you're at your worst, which is two 5Ks in parallel with each other, which is a 2.5K ohm resistance on the input. So if you sample them too quickly back to back, they will crosstalk with each other and things will not give you quite the answers that you think they should give you. So the right way to do these is you come over here and you go, I set the switch to that one, and then I wait a little bit, and then I take the sample. And then I set the switch to that one, and then I wait a little bit, and then I take the sample. And what you'll find if you play around with these in a setup like this, you get to a certain sampling rate and things start to go screwy and you can't.
So you just set yourself at a known constant and start creating a loop and seeing when you get
That's
solid
actually
data.
that's actually something else you can do. You can do this, and you can set that to ground, and you can set that to ground, so that they're isolated on all sides by grounds. And so when you get to that, you go from a 0 and you get a charging constant, but at least then these two probably won't be cross-talking each other. They might still be cross-talking each other, but they won't. If you set it, if instead of going here to there to here to there, if you go here to that ground and then back, and then to this ground and then back, you're basically shorting out that capacitor on the inside, and you're giving yourself a good reading. Important things. You're getting into the analog domain with these, and people don't realize how twitchy this shit is. They throw a lot of stuff together and they get stuff that works, but they're really on the hairy edge in a lot of places.
So reserving one to ground would be a great idea in this, and going to it every time before you read the other one.
Yeah. Yeah. It's a great idea. Now the other thing is, like I said, you should go over here, you stop, wait a minute, do it. Now if you're writing down at the bare bones, at the bare metal C code, like I usually do, and not use, so our Arduino library has an analog read. I don't know what it does.
Yeah, it has its own interpretation of a lot of this.
It will set the mux, and it will go do what it's got to do to make that thing work. And I don't know if it just does it and reads it, or if it does it, waits a minute, and then reads it. So if you're writing your own code down at bare metal, you want to make sure that you wait a minute and then read it. There's some other things, so, and now we're going to get into some other things that are important about how the ADC works internally, because it's not instantaneous. In the bad old days of PC joysticks, you have your joystick, which was exactly what I just drew, but it would come into the joystick port on your computer, and there was a big ass capacitor right there. And coming off of that capacitor was a switch to ground, and actually was that they didn't do this, they did that.
you did that. 5 volts in, and there's some variable resistance there. And there's a switch, and there was a logic gate or comparator basically, and that came back here to run the switch, and actually it didn't go back there to run the switch. It ran a latch on a counter. So you had a clock going into a counter, and this was latch. And then there was a reset pulse that reset this and reset that. That seems really complex. That is a cheap and dirty analog to digital converter. And analog to digital converters used to be really stinking expensive. Like 8 bits was, maybe $100. And so if you want a joystick for a PC, you got $1. You got back in the bad old days, $1, $5, $2. This is maybe the inside of your circuit's maybe $10 instead of $100. And so what happens is current comes through the resistor, hits the capacitor. There's an RC time constant, tau equals RC, and I've done the math on this. I'm trying to remember. I think it's 98% charged is approximately equal to 5 tau, or 5 RC. We'll just multiply R times C, and that gives you tau. 5 tau later, you're charged, like 98 or 99%. So what they do is they set this at like 4.5 volts or whatever. I mean, it's going to switch wherever it switches. And then you run a clock in here that counts. So this is just a counter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Click! Oh, okay, it got up to there. You were at 12. Okay, and you've got this reset set up to another timer here that knows, maybe it's 10 milliseconds is the longest this thing can go. Every 10 milliseconds, it resets everything, and now that thing starts at 0 again. 0, 100, 200, 300, 400, 500, but click. Oh, 500. I've got a cheap and dirty analog to digital converter. That's not how they work. That works, but it's dirty. It's bad, but it works. And if you're trying to save a lot of money, it's a great way to go. The way then they went to something called a flash converter, which inside had a little amplifier that was a unity gain amplifier. So your input came in here, and this isolated it from the rest of the world. And then it had a gob of resistors. If it was 8-bit, it was 255 resistors. If it was 4-bit, it was 16 resistors. And these all tied off.
This is before surface mount.
This is the first ICs. When ICs really start getting out, this would come out, and then you would get, if there's N bits here, there's 2 to the N resistors there. And so if you had, so remember we talked about the voltage divider equation, right? And these are all tuned so that it's linear. If I've got a 1/2 volt, this one's got a lot, this one has, if I've got a 1/2 volt here, this one's got, let's see, 1, 2, 3, 4, 5, 6. This one's got maybe 1/10 of a volt, and this one's got 2/10 of a volt, and that one's got 3/10 of a volt.
So yeah, what voltage you put in there based on what you read on the other side tells you what.
Yeah.
Oh my gosh.
Yeah, there's this huge logic cloud.
It's American Ninja Warrior, and you're going up that slope, and it's how far you get up that slope is where it caps off.
Yeah, but then you've got all this logic that's going to turn all these
Right.
into just 4 bits,
Yeah.
right? And they quit making flash converters. You can still buy flash converters, but I don't think you can buy one that's bigger than 8 bits because the logic got so freaking complex. Going to that 9th bit just uses up so much space.
Magnitude goes, yeah.
Yeah. So now, but flash are fast. I mean, from the time that you change this value here
to the time that bits come out the back end can be nanoseconds. I mean, they are screaming fast. And I mean,
I guess there's it's a timing. I mean, there's a baud rate effectively.
You've got this logic cloud. You know, it takes so many nanoseconds to go through a gate and this gate and that gate. So it goes in and it comes out the back end, and you're guaranteed that after this amount of time that data is valid. And so you just make sure you don't sample any faster than that. Grab. Great. Works great. You can find them. A flash is generally the most expensive kind of ADC you'll find. But you're paying for speed. But you're not getting 16 bits of resolution or 12 bits of resolution. What they generally do is...
So you couldn't use that in like audio because you need too many bits in like a...
Actually, 8 bits isn't bad. I mean, telephony.
Yeah. I meant like CD, CD players, that kind.
Yeah, they're 16-bit.
Yeah. So
I think they're 16-bit. So what they do now is you have an amplifier and you have a switch and you have a capacitor and you have a switch and you have a capacitor and finally you have a switch and you have a capacitor, and every one of these goes off to a piece of logic. And what you say is you close this, you open them all up and you close this one, and this capacitor gets a certain number of electrons charge on it. And then I open it up. And now I say, okay, and this, V is equal to the capacitance divided by the amount of charge in the capacitance. C is equal to QV. So these capacitors are generally different sizes. This one's big, this one's smaller, smaller. And and usually maybe half the size, or whatever this relationship is. So if I've got 10 electrons here, now I close this, and my charge is going to split evenly, so I'm going to have 5 electrons here and 5 electrons there. And now I'm going to open this switch back up. And I can see what this voltage is on these 2 points. And now I can do it again and again and again and again. And I can see by how much charge moves around, I'm handing charges, little buckets of charge back and forth, I can make a decision on how big my original signal was and how many bits it is. And then they figured out, well, I don't have to have 73 capacitors in here handing this all back and forth to do this. They figured out they can use a little state machine here that just hands it back and forth between these 2 capacitors. So it's more than 2, but they do this little game where they hand it back and forth. So what you see now on most analog to digital converters, and I'm going into this because you might someday want to interface an external analog to digital converter to something, is you'll have analog in, and you'll have a clock, and then you'll have 12 bits out, for instance, and then you'll have a strobe that says valid. And then there'll be some other stuff on there that goes with it. There's maybe an enable pin, maybe power. You're gonna have 2 power pins. You're gonna have 2 ground pins. This is analog VCC. This is digital VCC. This is analog ground. This is digital ground. Never should those 2 touch each other. Never, ever, ever, ever. And here you should have a ton of capacitance on it to keep noise off of it and everything else. We can go into a lot of stuff about circuit design with an analog to digital converter. But so now what happens is you'll go, this is called a pipelined ADC. So I'll send in a clock. I'm gonna write a lot of clocks up here on the wall. And I'm going to send an analog voltage in here. I'll be at this level, and then I'll be at this level, and then I'll be at this level. And there, 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 there. And I'm going to write my output down here. And instead of writing some digital number for it, I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, maybe 9, 10. My output is going to be this, and then this, and then that, and then this, and then this. So basically, my output is delayed by some number of clocks. And that gets a little twitchy because you read the data sheets and you're not sure if it means on the 10th clock that's valid, or does that mean it takes 10 to go through, so really on the 11th clock that's valid. And so then you end up with this stuff where you do a lot of experimentation to figure out, is that really what just came out of there, or is that not really what just came out of there? So, but what you'll see if you go down inside that microcontroller, something similar to this, where it's handing charge back and forth and playing a game in a really small amount of space, because that you can get a fairly decent analog to digital converter in a small amount of space, and if you don't do a lot of special design work to make it really, really clean. So that's the other thing we'll talk about, and then we'll basically be done for the night. I'll give you homework. That is that if I don't do a lot of good things to pre-process my analog signal on the way in and make sure it's driven and clean, then it has noise on it. So let's think about this. 5 volts divided by 1,023 steps. Somebody got a calculator?
Went to sleep.
I hope you get there before I do.
Oh my gosh.
0.004?
Yeah. 0.0048887.
That's 4.9 millivolts per count, or per LSB, least significant bit. 4.9 millivolts doesn't sound much, but that's the difference between a 0 and a 1, or a 255 and a 256. Or a 1,020 and a 1,021. It is not hard to get 10 millivolts. It is not hard to get 20 millivolts of noise on there, because you've got digital circuits running around. It's not hard. Now, the next part of that is a really good analog to digital converter can still run you $1,000. That clearly ain't $1,000 ADC. In fact, a really good enough ADC for a lot of things can still be $20-25. That whole board costs $25, so that ain't even a pretty good one. That is the cheapest ADC you can make in a digital process, because when you do analog circuits on chips, you use a different process than you do for digital circuits. There's a lot of things that go on in there, and so I'm going to tell you Generally speaking, I've got a friend who's done a lot of testing, and he says if you're really careful with them and you follow their design guidelines and their software guidelines, and then you be a little bit more careful than that, he says it really is pretty close to a 10-bit ADC, and you really can get 10 bits of data out of it. But my experience is the bottom, I'm not trying to be careful with my code most of the time. The bottom, at least 1 bit's noise. And it's just noise. It could be a 0, it could be a 1, whatever. And sometimes there's been a couple of things I've done where the bottom 2 bits are noise. So it's like, yeah, it's a 10-bit ADC, but I'm only getting 8 bits worth of data out of it. So a quick word on how that thing works in code. When you write code for it, that is actually 2 registers. This is analog low and this is analog high. I don't remember what the actual registers are called. I don't know if you can actually, I think you can access them directly. And so this is 8 bits and this is 2 bits and this is don't cares. When you write your C code, the C compiler all handles this and it stacks these and goes bang bang. But when you read your analog to digital converter, you need to send it an unsigned int. Because that's an unsigned int. That's 16 bits and there's no signed bit on it. Actually, you could send it a sign. You could just send it an int because it would have a 0 at the. It would most likely have a 0 at the lead. And then what you want to do is once you pull that in, you want to bit mask it. And so you want to say analog value, and then you want to say analog value equals analog read of the pin and 0x3f. That's a bit mask that's going to basically make those 0. So if there is trash in there, you throw away the trash. Is it double and? Maybe it's single and. Take a look. I can't remember which one's bitwise and which one's logical. It might be
probably single.
Yeah, I think it is a single and.
Double's usually logical.
I think that's the. So, homework 2. I want you to do analog read into a serial output. And I want all 6 channels. You only have to drive one of them. Drive at least one. In fact, drive at least one, but not all 6. So what I want you to do is I want you to just simple loop, set up your you got to set up your pins as inputs. You got to ensure that the pull-ups are turned off because you can actually turn the pull-up on one of those. You've got to, it's an input, the pull-up is off. You need to set the analog reference for the right voltage, and then you need to do an analog read of the right pin, of the correct pin, and then you need, when the analog read is done, I want you to write that out in a serial print statement or some print line out to the screen so you can see it. And what I want you to do is have, preferably is to have 1 pin on and 5 pin floating like we were talking about, and watch what happens. And then connect up something on a different pin, not the one right next to it, but maybe pin 0 and pin 4 or something like that, and notice that there's that time constant in between, and then it flips to something else. And if you want to put a pot on there and you play around with a pot, that's great, because that lets you kind of get a feel for how the pot works. But if you just want to tie it directly, because right here on the output, you've got or on your Arduino right there, you've got a 5 volt line, a 3.3 volt line, and over here you have an analog reference line, which I think is always 1.2 volts or 1.25 volts. So you can just jump a wire back between those three if it's on a 5 volt setting for your analog reference, and watch what happens. That's often what I do to test them out instead of trying to hook up a pot and everything else, because I don't have one sitting around. And those are your 2 homeworks. And we're done. And it's almost exactly 2 hours tonight.